5 report doing on slinkies since we had the option, and I thought it was cool. Alright, so introduction. The purpose of this lab was to examine and analyze the motion of a falling slinky and then create a computational model using the momentum principle. Some of the key physical principles involved include gravity, tension, drag. The tracker was used to analyze the video of the slinky, and the glow script was used to construct the computational model. A quick preview of my final results is that there were noticeable deviations between the observed data from tracker and the predicted data from the model. Okay. Next slide. The fundamental principles were momentum over time. We had the gravitational force, and then drag force. From this, we get the velocity and position update formulas, which allows us to calculate how the slinky's velocity and position change at each time step. These formulas come from the Newton's second law. And using all these formulas, we are allowed to predict the how the slinky accelerates and stretches and slows as it falls. Okay. So these are the procedures. I began by screen recording the following slinky video from YouTube, then I uploaded it to the tracker and marked the position of the slinky frame by frame. Then I created a computational model in GlowScript to generate the predicted trajectory. I collected data from both tracker and GlowScript, exported them into spreadsheets, and then compared the observed and predicted data in Excel. Okay, so these are the initial conditions. System, slinky, surroundings, air, earth, environment, whatever. Here's their mass, height. I just googled the professor's height to calibrate the thing. Initial position, velocity, drag constant. And I used this to find. I found this by trial and error. Whatever seemed the closest. Tracker analysis. So these are the conditions still. Nothing much has changed. Yeah. And the code, right? So I put the initial conditions, everything highlighted in orange. I found what the drag force was, put that in. Yeah, everything I just plugged in. Okay, and here's where it gets interesting. The code structure. This is for the first while loop of the model. The gravitational force is calculated using mg j hat, and the tension force is included as well. The velocity and position are updated using the standard update formulas. In the second loop, the gravitational force is reversed and the drag force is added. The net force and the sum of gravity and drag, and once again the velocity and position are updated. And I just sent a screenshot of the GlowScript output right here. Observed versus predicted graph. So similarities, both did follow almost the same trajectory. The dip appears in both curves. The observed orange line starts slightly higher, which of course makes sense. And then some deviation in the middle region over here. And those could be because of sources of error. Clicking slightly off the slinky, especially over here. Maybe the approximations weren't completely accurate. But yeah, that's the experiment right there. So I'll begin discussing it. So does the bottom of the slinky stay stationary? Yes, the bottom stays nearly stationary right after release because the tension in the stretch coil holds it up. It only begins to move the collapsing motion from the top reaches it. Once the collapsing motion of the top reaches it, okay. And if the slinky were twice as heavy, would the bottom still stay stationary? Yes, the behavior depends on the tension distribution and not the weight. Even with double mass, the bottom would still remain almost stationary until the collapse reaches it. And the momentum principle model produces a trajectory similar to the motion. Differences mostly come from I'm thinking tracking inaccuracies and modeling assumptions. The falling slinky demonstrates how tension propagates through the slinky before the bottom begins to move. Alright, that's my experiment.